Hello everyone, welcome back. If you are new here, please consider subscribing to our channel for more insightful videos about computer programming and software engineering. Today we are going to discuss and compare the two most fundamental data structures we have discussed so far, the arrays and linked list data structures. So let's get started, but before that let's refresh our memory by defining data structures. What basically data structures are. In computer science, data structures are a way of organizing and sorting the data so that they can be accessed and work with efficiently. So data structures define the relationship between the data and the operations that can be performed on this data. Among the different data structures, array and linked list serve as the foundation for many other data structures. In the previous video, we learned about arrays and arrays data structure and its advantages, and also we discussed about array shortcomings. We also explored how a linked list data structure can overcome the disadvantages of an array data structure. Now you might be wondering when to use an array or a linked list data structure, which one is better. So to answer this question, when we compare two or more data structure, we cannot definitely state that one data structure is superior to another data structure. The choice of the optimal data structure relies entirely on specific requirements and tasks at hand. In certain situations, an array may provide advantages, while on other scenarios, a linked list data structure may be more suitable. Furthermore, the selection of one data structure over another data structure depends on the type of operation performed on the data structure, or the type of operation we frequently perform on the data, and also it depends on amount of or size of the data we have in hand. So in this lesson, we will conduct a comparative study of the advantages and disadvantages of these data structures. Our goal is to gain an insight into specific scenarios where an array or a linked list might be an appropriate choice. We will mainly talk about the simplicity of these two data structures, array and linked list. We will talk about size of these data structures and also memory utilization. Then we will discuss about accessing cost, or how much time it's going to take to access an element, searching algorithms we can perform on these data structures, and also finally we'll be talking about insertion and deletion time complexity of these data structures. Talking about simplicity, definitely array data structure is much simpler for beginners to learn than linked list data structures. But once we learn the core concepts in a linked list data structure, we will understand how beautiful and efficient a linked list data structure is. So arrays and linked list data structure each have their own advantages and disadvantages. The selection of one over another depends on different factors, as we mentioned. Let's begin comparing and contrasting these two fundamental data structures and discuss the benefits and drawbacks of each of these two data structures. For those of you who haven't watched the array and linked list discussions, first let's understand what each of these data structure is before we move to their comparison. So defining an array, we define an array. An array is a type of data structure that can store fixed size sequential collection of elements of the same type. In other words, it is a homogeneous data structure that can store only data of the same type. An array is used to store collection of data, but it's often more useful to think of an array data structure as a collection of variables of the same type stored at contiguous blocks of memory. The simplest data structure in a linear data structure is a linear array, also called a one-dimensional array data structure. We also spoke about linked list data structure. We defined a linked list as a linear data structure, but unlike arrays, it does not have a fixed size. It is a dynamic data structure that can grow or shrink at runtime. Elements in linked list data structure are not stored in contiguous blocks of memory like arrays. The elements in a linked list are stored in random locations or not contiguous memory locations. Also, the elements in a linked list are linked using pointers to another elements. Also, each element or each node in a linked list have two parts the data part and the link part. Data part is used to store the actual data, and the link part is used to store the address or memory address of the next or coming node. Now that we have a basic understanding of what array and linked list are, let's dive into their differences. This comparison will help you decide which data structure to use when you find yourself in the crossroad of selecting one data structure over another. So first, let's talk about size. Arrays are fixed size. This means when we declare an array, you must specify its size, and the size cannot be changed later on. So say I have this array called A. To define this array, I need to specify the size of the array ahead of time or at the compile time. So say I want to define an integer array called A, new int of, say I want to store 7 items. So the size of the array is fixed, and this cannot grow or shrink over the time or runtime. On the other hand, linked lists are dynamic and flexible data structure. They can grow or shrink at runtime as insertion or deletion operations are performed on them. So we in the previous video we saw that linked list is made up of different nodes, and each node are connected to each other via pointers, and we do not have to define the size of the array, the size of the linked list, unlike array data structure, ahead of time. So we can insert as many data we want in a linked list, or remove as many data as we want. Then let's talk about memory utilization. Talking about memory allocation and utilization, arrays, as they are fixed size and the elements in array are stored in contiguous blocks of memory, they can lead to inefficient use of memory if the array size is overestimated. We give the size of the array at compile time, as we just saw, or when we declare an array, we give the size. We estimate the size of the array in the cases we don't know how many elements to store in the array, so we just guess and estimate the size of the array. But in the cases if we overestimate the size of the array, say I want to estimate I will be storing 1,000 values, so I define an array of size 1,000, so 1,000 blocks of memory will be allocated for my array. But if I ended up storing only 10 values in my array, so only 10 values is stored, this much blocks of memory is used, and this much blocks of memory is allocated. 990 blocks of memory is allocated, and they are unused. So there we have a big wastage of the memory. Same case if we underestimate the size of the array, say I estimated storing 10 values in my array, but at the runtime the user want to store 12 or 100 values. We cannot do that, because once the array is full, we cannot insert more values to the array. So these are the drawbacks with arrays in terms of memory utilization. But on the other hand, linked lists, because they are dynamic in nature, utilizing memory is efficient, as nodes are created only when they are needed. Unlike arrays, we don't have to initially declare the size of the linked list. We can simply add nodes as they are needed. So if we have a linked list with size 3, so I can easily add elements in this array at the beginning, or at this linked list at the beginning or the middle, without worrying about the size or shifting elements. So if I want to insert an element at the end of this linked list, I can create a node, and this node may have, say, address 1,000. So I can just simply, instead of storing null here, I can store the address of the newly created node here, and they will be linked, so I can have access to this newly created node. So in terms of memory utilization, there is no memory wastage, and memory allocated as they are needed, and they are deallocated as they are not needed. So if I delete this node from end of the linked list, so the memory will be deallocated. But in the case of arrays, if the array is full, but if I want to delete like half of array elements, so there will be no elements stored in this half of the array. These blocks of memory is already allocated, and they will be there even if we don't use them. These memories will be wasted. But that's not the case with the linked list. As we delete node or an item from linked list, so the memory will be released so that we can use it later on. But if I want to delete another node from a linked list, I can do that easily and the memory will be released. One thing to mention that linked list data structure requires a little more memory than an array data structure, because we have to store a pointer to the next node beside storing the actual data. So in memory, in terms of memory requirement for storing the same amount of data items or the same number of elements in an array data structure is less than memory requirement for that of a linked list data structure. So as we saw in the previous video, beside the storing actual data in a linked list node, we need to store additional information for storing the pointer or memory address of the next node. So if the data takes 4 bytes, we have to store 4 more bytes in each node to store the address of the next node. But in terms of memory utilization, linked list is better than array data structure, because a linked list is a dynamic data structure and we don't have to define the size of the linked list data structure ahead of time, and we don't have to worry about overestimating the size of the data structure or underestimating the size of the data structure. So in terms of memory utilization, array is worse than a linked list data structure. But when talking about memory requirement, array data structure is better than linked list data structure, because in array data structure we don't have to store extra information beside the actual data we need to store. So the memory overhead with arrays or less than compared to array data structure. But when it comes to storing complex or large data having large size, then a linked list would be better choice than array in terms of memory utilization or memory requirement, especially in cases where we don't know the number of items to be stored in advance. So if we overestimate the number to store in case of array, we will be wasting a lot of memory. So let's consider this student type or user defined type called student. This students have integer value ID. This integer is going to take 4 bytes of memory location. Then we have a string name, though we cannot specifically calculate the size of the string because it depends on the number of characters in a given name. So let's assume a name will take 12 bytes of memory location. Then we have integer age. This is again going to take 4 bytes. We have long GPA. We know long takes 8 bytes of memory location. Then we have letter grade. A character takes 2 bytes of memory location. So to calculate the overall size of this user-defined data type student, that's going to be 4 plus 12 is 16. 16 plus 4 is going to be 20, 28, and 30. So a student data type or a variable of types or an object of this type student is going to take 30 bytes of memory location. Say I want to define an array of type students, so I can do students, array of students, let's call it students, equal to new student. Say I want to define an array of 10 students. So this array is going to take 10 into 30, since each student takes 30 bytes of memory location. So this array will take 10 into 30 equal to 300 bytes of memory location. But if I ended up storing only 3 students here, 1, 2, 3, S1, S2, and S3, so I only used this much portion of memory, so I used only 3 into 30 is going to be 90. I only used 90 bytes of memory location, but I ended up wasting 210 bytes of memory location. But in case of a linked list data structure, I would create a node having a data part. So in this data part, I store a variable or an object of type student, say S1, and then I'll have a pointer pointing to another node. Say I have another node here storing S2. I have another node here storing S3. Say this one has 100 memory address of 100. This way, say have address of 200, so I can store 200 here, and this may have address 300, so I can store 300 here. So beside the 30 bytes of data here, I store 4 extra bytes of memory location. So each node in terms of a linked list will take 34 bytes of memory location. If I store 3 students, so 34 into 3 is going to be 3 into 4, 12, 102 bytes of memory location. So in compared to array, we stored 12 more bytes, but we haven't wasted 210 more 10 bytes. So only 102 bytes are used, and we didn't end up wasting a lot of memory. So generally talking, memory utilization with linked list is better, where in some cases memory requirement is better with array data structure, because we don't have to store extra information other than actual data in array. So in other words, memory overhead with array data structure is less. But when it comes to complex data, storing complex data types such as a student, then I would say linked list would be a better choice to store data, but store data in a linked list, because if we ended up overestimating the size of the array, we will be wasting a lot of memory. Next, let's discuss accessing element from these data structures and the time complexity associated with accessing item in array and linked list data structures. In array, accessing an element is done by referencing its index values, the index value of each item. This allows for constant time access, which means accessing any elements in the array data structure takes the same amount of time regardless of its position, or regardless of the position of the item in the array, or regardless of the size of the array. The time complexity for accessing an element in array data structure is always constant or big O of 1. We defined that when we define an array, so contiguous blocks of memory will be allocated by memory manager, and the name of the array is going to point to the first the memory address of the first element in the array, or the name of the array is a pointer to the first memory location allocated to the array. Using the base address or the first address, we can easily calculate each element at a given index value. Say I want to calculate the memory address of each element, an element at index I, so I can do that using base address. So the given base address, for example, here is 100, so I can take the base 100 plus I into the size of the data I have stored. In this case, I have stored integer value, so the size is 4, I into 4. Say I want to access the memory address of item at index 5, so what I can do, the value of I is 5, so 100 plus 5 into 4 is equal to 120. So the memory address of item at index 5 is 120. So using this simple calculation, we can access the address or memory address of any element in constant time, or big O of 1. So random or direct access is possible in an array data structure as long as we have the base address or the address of the first element, and this operation is going to take big O of 1 or constant time complexity. On the other hand, in a linked list, accessing an element requires traversing the list from the beginning until reaching the desired elements. This process takes linear time complexity, or big O of n, where n is the size of or number of elements in a linked list. As we discussed, linked list items are not stored in contiguous blocks of memory. Say the first element is stored in memory address 100. So the second is stored in 200, and the third element is stored in 300. So these are not contiguous blocks of memory. We cannot randomly access or calculate the memory address of each element using the base address like arrays. So to search an item in a linked list, we have to use the head pointer. As we said, head pointer is just a pointer pointing to the first node in the linked list. So this head pointer is going to store memory address 100. Using this memory address, we can reach to this node having number 3. Say we want to search for item for 8. So what we can do using head pointer, we can jump to this memory address and check if 3 is equal to 8. No. Then this using this nodes pointer section that points to the next memory location, we can jump to the next memory location and check if 5 is equal to 8. That is not. Then using the pointers of this pointer of this node, we can jump to the next node or access the next memory location, and we check if 8 is equal to 8. Yes, we found the item. So to find an item in a linked list, we have to start traversing from the beginning, going all the way up to end, or up to when we find the desired item. So this is going to take a big O of n, or linear time complexity. In the best case scenario, if the item we are searching is the first element or the first node, then in that case we will have a constant time complexity, because we have the item at the beginning of the list. But what if the item reside at the middle of the element? In that case, we might have to traverse n by 2, or half of the linked list. That's going to be big O of n again. What if the item resides at the end of the linked list, or it is not present in the linked list? We have to, in that case, start traversing from the beginning and go all the way up to end of the linked list. So in this case, it's going to take big O of n time complexity, or linear time complexity. So while computing the time complexity of an algorithm, in this case search algorithm, we always consider the worst case time complexity. We don't consider the average time complexity or the best case scenario. So that's why searching for an element or accessing an element in a linked list data structure takes big O of n, or linear time complexity. Therefore, array data structure provide more efficient access to elements compared to linked list data structure, as they offer constant time access. However, linked lists have their own advantages, such as efficient insertion and deletion of operation that we will be discussing later on. Now let's talk about the search algorithms that we can apply or perform on these two data structures. There are basically several searching algorithms that can be performed on array data structure and linked list data structure. Here we are going to mention some of the most commonly used searching algorithms. For array, we can perform a linear search. It is basically sequentially checking each element of the array until a match is found or end of array is reached. So in a linear search, we start from the beginning of the array and we go all the way up to end of array. Either we reach end of the array and we didn't find the item, or we found the item at the end of the array or at the middle of the array. So in worst case scenario, a linear search is going to take big O of n in the array data structure. Then we can perform binary search on array data structure. It requires array to be sorted. We saw how to perform a binary search on array data structure. It basically it repeatedly divides the search space in half until the target value or the target element is found. So in the binary search algorithm, we can have in worst case scenario big O of log n, or logarithmic time complexity. For linked list, a linear search or sequential search is possible. As we said, when we want to search for an item, we start from head and go all the way to end of the list. So this is called linear search or sequential search. This takes big O of n, or linear time complexity. Binary search is not possible with the linked list data structure, because the items are not contiguous, and we cannot calculate the mid element to half the data structure each time. So then we can perform recursive search on linked list data structure. The recursive search uses a recursive approach to search for the target element in the linked list. A recursive search also takes big O of n, or linear time complexity in the linked list. So in the later videos, we will see how to linearly search for an item in a linked list data structure, and also how to recursively search for an item in a data structure. It is important to note that the efficiency of this algorithm may vary based on the size of the data structure and the specific element being searched. Additionally, for arrays, binary search can only be performed for, as I mentioned, on sorted arrays. Now let's talk about the time complexity with insertion and deletion operations. In terms of insertion and deletion of elements, linked lists perform better than arrays. In an array, insertion or deletion of an element requires shifting all elements, which can be costly in terms of time complexity, especially if the array is larger and larger. However, in a linked list, insertion and deletion can be performed easily and quickly by just updating few pointers. And if we have already the pointer to a location we want to insert or deletion from, then the insertion or deletion in linked list data structure is going to take constant time, or big O of 1. So let's break down the insertion and deletion operation and examine each operation at the beginning of the data structure, at the middle of the data structure, at the end of the data structure. So first let's examine insertion at the beginning. So in the case of array, if you want to insert an item at the beginning of the array, we saw we need to, when we want to insert an item, say I want to insert 10 here, what we have to do, we would shift all elements to the right by one index to make a room for the new item. In that case, the time taken to perform this operation is going to take big O of n, or linear time complexity, where n is the number of item we have to shift to the right to insert an item at the beginning of the array. So in the case of linked list, if we want to insert at the beginning of the linked list, since we have a pointer or a head pointer pointing to the beginning of the linked list, so we can easily create a new node having data part and pointer part. So say I want to store number 10, say this newly created node has an address of 1000. So what I can do is I can store the memory address of the head to the next part of the newly created node. So the newly created node now is pointing to the head pointer, and finally I can update my head pointer to point to the newly created node. Instead of storing 100, so it's going to store 1000. So this way, by changing few pointers, we can easily insert an item or a node at the beginning of a linked list. So for the linked list, this is array, and for the linked list, insertion at the beginning is going to take constant time, or big O of 1. Then let's talk about insertion at the end of the data structure. So in the case of arrays, since we can access the end of the array in constant time, so we can easily access this index value at constant time. We can insert number 10 here, and the insertion at the end of array in case of array is going to take constant time, or big O of 1. But in terms of linked list, to reach to the end of the linked list, we have to start traversing from the beginning of the linked list using the head pointer, come here and go all the way until we read the null terminated node indicating the end of the pointer. Then here we can easily create a new node having a data part and a link part. Say I want to insert number 20, so this is going to be null initially. Say this address, this newly created node may have an address of 250. So what I can easily do, once I reach the end of the array, I can update the pointer of the last array pointing to the newly created node. So I can store 250 here. This way we can insert at the end of the array. So in this case, insertion at the end of a linked list is going to take big O of n, or linear time complexity. But we can bring this time complexity to constant time complexity if we have kept a tail pointer pointing to the end of the node. So say each time I inserted a node, let me delete this one also. So initially I kept a head pointer, this is 100. When I inserted first node, so I kept a pointer pointing to this head node. Also, if I keep a tail pointer each time I insert the node, so initially tail pointer is also pointing to the first node. But when I insert the second node, what I can do is I can update my tail pointer pointing to the next node. So by inserting the second node, I can move my tail pointer and pointing to the second node. So tail pointer comes here. Then when I insert the third node, I keep the head pointer to the first element, but inserting another element, I can move the tail pointer pointing to the end of the list. So this way, if I keep a pointer to the end of the list and also to the beginning of the list, insertion at the end and beginning of the list is going to of a linked list is going to take constant time, since we have already a pointer to the end of the list, and we don't have to traverse from beginning going all the way to get a pointer to the end of the linked list. So using the tail pointer, I can easily update few pointers and insert at the end of the linked list. In that case, both insertion at the beginning and at the end of a linked list is going to take constant time. Next, let's discuss the insertion at the middle or ith position of array data structure or linked list data structure. So middle or ith position. To insert an element at the ith position of array, say I have this array and having 5 here, 8 here. So I want to insert an item at index 2. What I can do is I first shift each element to the right to make room for the new item to insert. Once I reach this index position, I can easily replace this 8 with the new index. So 8 will go to index 3 and 10 will go to index 4. 5 will go to index 5 and 8 will go to index 6. So this way I can insert an item at the middle or ith position of an array data structure. This operation, since I need to shift n element to the right, this operation is going to take big O of n, or linear time complexity, where n is the number of items we need to shift to the right. But in case of a linked list, I also need to start traversing from the beginning of the linked list until I reach the position where I want to insert the item at. So once I reach the position, say I want to insert a new item here, what I can do is I will create a new node. Say I want to insert number 20. Say this has 3000. So what I can do is instead of this pointer pointing to 300, I will change this pointer to point to 3000, and this pointer, instead of pointing to null, I will have it to point to address 300, and this will point here. This pointer will be broken. So this way I will be able to easily insert at a given location or ith position of the linked list. So this is going to be null. Since I need to traverse over from the beginning up to the end position, so I need to traverse n items. So this operation is going to take also big O of n, or linear time complexity. But in cases if I have a pointer to the index position or to the location where I want to insert the item, in that case then insertion at that position is going to take constant time, or big O of n, since we have to only change and reassign few pointers. But if we don't have the pointer to the index location or the position where we want to insert the new item, in that case we would need to traverse until we reach the position. This traversal takes big O of n, where n is the number of items we traverse until we reach the position in which we want to insert an item. Now let's talk about deletion operation on linked list and array data structure. Again, we are going to break it down into 3 type of operation: deletion from beginning, deletion from end, and also deletion from the middle of the data structure or given index position. In the case of array data structure, if I want to delete an item from the beginning of the list, say I want to delete number 3 here, so what I can do is I will to fill this gap, I will need to shift each element to the left. So 5 comes to index 0 and 8 goes to index 1. I have to shift all the elements. In this case, since I need to shift n elements, this operation is going to take big O of n, or linear time complexity, where n is the size of the array or the number of items we need to shift to the left. But in case of linked list data structure, if I want to delete from the beginning, what I can do is I just update the head pointer. Right now head pointer is pointing to first location, which has address 100. What I can do is I will update the head pointer to point to the second node. The second node becomes the head pointer. So instead of storing 100, so I make head pointer to store address 200. So this connection is going to be broken, and this connection is going to be broken. Since this node is not pointing to anywhere, it's eligible for garbage collection, and this will be collected by garbage collection, and the memory will be released. So this way I can easily delete an item from the beginning of a linked list by reassigning few pointers. So this operation is going to take big O of 1, since I don't need to shift any elements. I just only need to update the head pointer to point to the second element. Next, we have deletion at the end of the array. Say I have number 5 here, and my array is 4, and if I want to delete number 8 from end of the array, I can easily delete that, and I don't need to shift any element since I delete from end of the array. So this operation is going to take big O of 1, or constant time complexity. And also I can access the last element directly by its index value, so it's going to take constant time complexity. But in terms of linked list data structure, in order to get to the last element, I have to start traversing from beginning of the list and go all the way up to end of the list. To make this pointer, I have to traverse all the way from the beginning to the second last node. So I have to make this pointer pointing to the null instead of pointing to address 300. So this will be broken, and the last element will be eligible for garbage collection. Since we traverse from beginning of the linked list going all the way up to the second last element, this operation is going to take a big O of n, or linear time complexity, where n is the number of item in the linked list. Next, we have deletion at the ith position, or the middle of the element. Say I want to delete this item at index 3. What I can do is I will copy all or move all the elements at one index to the right, to the left. So this operation will take big O of n, or linear time complexity. Whereas in the case of linked list, if I don't have a pointer to the position where I want to delete, I have to start traversing from the beginning of the list until I reach the position I want to delete. So once I reach, I can delete this item and make this node pointing to the next node. So instead of storing 200 here, I will make this node store 300. Since we traverse from beginning and going all the way until we reach the position from where we want to delete, this operation is going to take big O of n, or linear time complexity, where n is the number of items we traverse until we reach the position from where we want to delete. So to summarize, both arrays and linked lists have their own pros and cons. The choice between them depends on the specific requirement of the program you're writing. If you know the size of the data you're dealing with and you need fast access of the element to any position, then array would be more suited for this task. Conversely, if you need more flexibility with size and perform a lot of insertion and deletion, then linked list would be a better choice for you. So let's do quick revision of what we have discussed today. Array and linked list both are linear data structures. Array have fixed size and they are stored in contiguous blocks of memory and provide fast access to their elements, whereas linked lists are dynamic or flexible data structure. They allow efficient memory use and they provide fast insertion and deletion, and also their items are not stored in contiguous blocks of memory. And with that, we have come to the end of this lesson. I hope this comparison of array and linked list have been helpful for you guys. Keep in mind that there isn't the best data structure. The choice entirely depends on the situation, the type of data, the size of data, and the operation you want to perform on the data. Thank you for watching. If you found this video helpful, please give it a thumbs up and share with your friends. If you have any question or need further clarification, please drop comment below, and don't forget to subscribe to Code with Cougar, and see you in the next video. Bye bye.